Good afternoon, everyone. My name is Xiaolin Zheng. I'm a professor in energy science and engineering, as well as mechanical engineering. Today, I'm very excited to share my passion for fire and to discuss the roles of combustion in a sustainable future. My own fascination of fire began with fireworks. So when they light up the sky with vibrant colors and exciting sounds, it brings me immense joy. I often wonder, how do fireworks shoot up so high into the sky, and where do those wonderful colors come from? Fireworks relies on combustion, the chemistry and the physics behind how things burn, how gases expand, and how heat generates color and the sound, all contribute to the beauty of fireworks. And the fireworks is just one type of fire. Human has long been drawn to fire. In Greek mythology, Prometheus stole fires and gave it to mortals. And Zeus considered this a great crime and punished him by chaining him to a rock and let eagles feast it on his immortal liver. This story highlights the importance of fire to human. Indeed, fire is one critical ingredient made us human. Comparing to chimpanzees, we're at a disadvantage. Humans have shorter digestive tracts, weaker jaws, and smaller teeth. So how can we gain enough calories to feed our bigger bodies and energy-greedy brains? The answer is cooking with fire. When we cook food, it breaks down the food, making them easier to be digested and absorbed by human body. And those nutrients enable us to grow larger brains and also give us the time and the capacity to learn and innovate. So fire is a critical component to make us evolve as a human being. In addition to that, mastering fire is also important for technological revolutions. The invention of internal combustion engines fundamentally transformed our human society. Those engines powers cars, ships, airplanes, and enable the mass production and the global trading of goods. It transformed our lifestyle. But at the same time, they created a challenge for us. They create enormous amount of greenhouse gases by burning fossil fuels in those engines. So fires in those engines with that precision control reshaped our lifestyles and environments in both a positive and a negative way. Now we're at a crossroads. With the transition away from internal combustion engines to electrical vehicles, the question arises, what are the roles of combustion in sustainability? Is combustion irrelevant now? The answer is no, quite the opposite. In the foreseeable futures, when we think about cargo ships, airplanes, space propulsions, they will continue to rely on engine-based technologies, not batteries, simply because batteries do not have the high enough energy density needed for those applications. However, we'll see a transition from burning fossil fuels to sustainable fuels and e-fuels, such as hydrogen or ammonia or natural gas. The use of those new fuels create new questions. How do we make them, transport, and store them? How do they ignite and burn? What kind of emissions do they generate? All of those requires new research. So my group is working on producing hydrogen electrochemically, either using hydrogen as a fuel or as a feedstock to making other sustainable fuels. Beyond transportation, combustion finds many new applications in this sustainable society. From combustion synthesis of critical materials needed for fabricating batteries or fuel cells, to use fire as a reactor to recycle rare earth materials or critical materials from batteries or magnets. And also, with the rise of EVs, we see the increasing of battery fires, similarly with the wildfires And all those things raise the question about combustion safety. Let's first look at the combustion synthesis. Let's think about the transition again away from the engines, and we're either going to use batteries or fuel cells. But in all those energy devices, they contain a lot of metal oxides. For example, in batteries, the cathode material are lithium metal oxide. And in high-temperature fuel cells, from anode to electrolyte or cathode are all made of oxides. So to meet the global demand, the question is, how can we synthesize those metal oxides with the desired morphology and the composition in a scalable and economical way? Combustion synthesis is one possible solution. To think about the barbecue in your backyard. It cooks food very fast because it has very high temperature. And it's very scalable. You can have a multi-burner barbecues to cook a lot of food at the same time. It's economical, it's ubiquitous. Almost all of us can afford a barbecue, a burner or two at home. And we can apply the same principle for material synthesis to cook the materials in the flame. By precisely control the temperature, the gas composition, the flow field, the pressure in the flame, that allow us to control the environment for material synthesis. Here are some images about the materials we have made by combustion synthesis, and they range from nanowires to nanotubes. That's the carrots, and that one is the pipe cleaner. They're not just for beauty purpose. Those morphologies and their compositions are tailored for their applications, and they show excellent performance in their desired applications. One of the materials we are currently focusing on for hydrogen production is called high entropy oxide. It looks like a colorful candy made of different flavors or metal cations. The mixing of those diverse metal cations increases the entropy of this material. And that high entropy stabilizes the material for application. And that's essential for the durability of the device that employ those materials. So to make this high entropy oxide, the way we do is to mix the precursors in a solution phase, almost like making a soup, mixing all the ingredients together. Then we burn the soup in the flame. That high temperature flame breaks down the precursors simultaneously and fuse them together into this high entropy material. In addition to durability, one fascinating property about them is the tunability. For example, if we think about this as a catalyst for electrolyzers, taking that blue ball as the active site, the activity of that blue atom will depend on the neighbors. Suppose you have 5 neighbors, and it can be occupied by 5 different metal cations. So by permutation, there are 120 configurations. And that leads to 120 different catalytic activities. So this mixing with different composition in different proportion offers us an enormous knob to tune the properties, not only for catalysts, but also for other properties. Go beyond combustion synthesis, we can also think flame as a reactor for material recycling. As we all see, the lithium-ion battery demand is increasing exponentially, not just for EVs, but also for consumer electronics. We all own a few lithium-ion batteries, or if multiple, right, in scooters, etc. But to make those batteries, mining precious metals to support this is a broken system. This cannot meet the demand for making of the global lithium-ion batteries. One solution is to recycle. If we can treat those spent batteries as the ore and mine out the precious metals and use them back again to make the battery, then we close the loop. However, only about 5% of EV currently are being recycled at a global scale. The reason is recycling them is very energy intensive and chemical intensive, and it creates a lot of greenhouse emissions. A typical recycling process involves collecting of the batteries, transport to the point of treatment, and the treatment involves 2 steps. The first step is a very high temperature metal smelting process, and that takes a lot of energy and creates a lot of CO2 emission. Followed that is a leaching process that uses a lot of chemicals. What we are doing is to address the metal smelting process by using the energy left in the battery. So in this video, what you're going to see is when we mix the the cathode material in the battery with the aluminum current collector next to it, they are a very reactive material. So when we ignite from the top, this reaction generates heat and self-propagate. And this reaction changed the nature of the metal involved and made it easier to be leached for the following step. So combustion synthesis only requires 1 spark. It offers the promise to save energy and reduce emission for recycling. And this same type of idea can be applied to rare earth recycling from magnets. Not all the fires are desirable. We see news with batteries, cars on fire all the time. In parallel, due to the climate change, we're seeing increased frequent wildfires. And these two actually offer similar questions for research. What are the ignition properties, either of a battery or of a plant? For example, temperature, how they change with the humidities, compositions, and how fast does the flame propagate, how much heat it can generate. In addition, what kind of pollution it can generate from those smokes. Those are new type of pollutions we have not looked into. And those pollutions can have a huge impact in the air, soil, and the water. Charles Darwin has famously believed the 2 most significant achievements in human history are language and fire. In the field of language, we're experiencing a revolutionary phase due to the development of large language model. I believe fire is going through a similar phase as we're transiting away from burning fossil fuels to renewable resources. I believe combustion science is an essential part for powering sustainability. I'm truly thrilled to be part of the Stanford Doerr School of Sustainability, and I look forward to work with many of you on those important questions. Thank you.